Hi, welcome to Hamago that's hanging out, messing around, and geeking out with Arduino. And today we're going to learn about the Copycat drawing robot. So, Nancy and Cappy, do you want to introduce yourselves and then just get started? And maybe I will interrupt with questions, and maybe I'll just listen, and maybe other folks will show up. There's a text chat that's available. We go over to the left margin, one of the tools that you can use here. So take it away.
Cool. I'm Nancy.
Happy.
We both graduated about a year ago and started immediately working on our own idea, which is sort of this drawing robot arm coupled to an online class. So I guess today we'll be talking a little bit about sort of the different types of drawing machines that are out there, and then ultimately our own super like beginner-friendly robot arm method of approaching how to make a drawing machine.
Okay, take it away.
Sounds good. So I guess as a quick demo or something that is one way of approaching the problem is this sort of robotic drawing arm. And okay, so there are two parts to it, and you probably want to hold that higher. But as you can see, or we can do it vertically. So as you can see, basically what is happening is we have a control arm, and it's being copied by this copycat arm, which is controlled by motors. So this is our approach to a drawing robot arm, which is a very robotics-based approach. But actually, if you look at the history of it, there's like a lot of drawing machines out there. There's like the what are some drawings? Okay, so there's pantograph. Do you want to explain the pantograph?
Right. It's basically like a handwriting machine where you would write one thing and it copies it down for you, or copy like you can write multiple copies at the same time. It's just a set of like linkages. So you hold one pen and it moves an additional pen.
So it was like an entirely mechanical way of copying what you're doing. So it's been around for centuries. There are other drawing machines which are also mechanically based, which tend to make more artistic sort of renditions, like spirals or sort of circular patterns. I forget the name of what it's called. There's one on Kickstarter recently, which is based on a pretty old design. And the idea is that you have these set of waterways which are balanced pretty carefully. And then through a set of linkages, they create these sort of swooping patterns. So this would probably also classify as a drawing machine. And then there are a lot of like high-tech drawing machines that use KUKA robot arms. So KUKA is the name of this like robotics company that does really, really cool robot arms. They're also absurdly expensive. Probably tens of thousands, maybe hundreds of thousands of dollars. But they do really cool sort of like portraiture stuff. They can do really precise motions. And so say that if you are looked into drawing robot arms, there are these sort of really intense, like 6 degrees of freedom robot arms. So degrees of freedom just means like how many sort of like motions you can have. So like for instance, let's just take an example. I guess like for instance, this thing has this can move, and then this can move. So you sort of tend to consider it to have about 2 degrees of freedom. So this is like a 6 degree freedom robot arm that can draw like portraiture of people. So you have an algorithm that like looks at the face or takes a picture and then transfers that into something, a series of vectors that a robot can draw. So going to IME first. Okay, we're going to transfer. There we go. You can probably join it. Yeah. So that's an example of a robot arm drawing. And so when we started this project, it was sort of like how simple can we make a drawing robot arm? And as it turns out, you can make it very simply, as long as you have two servo motors and like popsicle sticks, you can make something draw. The challenge is making it draw something that is recognizable or draw in a precise fashion. So for instance, it's like pretty straightforward to do this sort of thing, where you can see you have the rotation sensor, the potentiometer. You can see what it looks like from the side like that. So you have these sort of rotation sensors, and you lead it into a microcontroller, and then
So it's essentially you've got a potentiometer that you've put a little piece of wood around the control knob, and that's your motion sensor?
Yeah. So the basic idea is that if you grab it at the tip right here, you would be able to draw like circles or things with it, and then the servo-driven arm would then copy these movements exactly. So yeah, that's the basic concept. We should fix the code. But so the basic idea is you're just mapping your sensor inputs to your servo motor outputs. So for instance, if I pulled the power on this, you can see that I can move this potentiometer arm, but then the servo arm won't mimic it. So it's entirely code driven. And so it's fairly straightforward to do something like this. It's like maybe 10 or 15 lines of code. I guess we could link to the code. So it's maybe 10 or 15 lines of code. So what we actually tried to do is to make it pretty straightforward as well to make more precise movements.
This is Arduino code we're talking about here?
Yeah, sorry, I lost it. Oh, no.
Can you do screen sharing and show us some code?
Oh, sure, absolutely. Okay, so one of these. Okay, so is it screen sharing?
Yes.
Oh, okay, cool. So this is our GitHub repository. You can go to it. It's public, and it contains all of the source code for everything we've done. So here you can see an example of a software program we've written where you draw on the screen, and then the robot arm mimics what you draw on the paper. And so in terms of the actual code, right now the code repository is still incomplete, but the basic code is there for the one with the two servo arms. So you can see here, you include the servo library. So I guess like a brief explanation of what a servo motor is. It's a motor, and basically it just has a little feedback mechanism inside it so that you control position instead of velocity. So in this case, you input the servo library, which gives you some servo functions. You have your floats and ints for keeping track of your the variables you care about. You patch it, and then this is all you do is you read in the value of the potentiometer and store it as your theta value. But it's not really in the correct theta units because the potentiometer is out of 1023, and your servo wants values from 0 to 180. So you do a bit of scaling, and then you just write it to the servos. Because the servos have that feedback mechanism, so you can just tell them which degrees you want. So that produces the behavior that we just demonstrated. Yeah, I guess this is, I don't know, should we go more into like other types of drawing machines, or should we just talk about robot arms?
Can you hear more about our robot arm or other robot arm?
Is it lagging? Maybe we should stop screen sharing. I don't know how to stop screen sharing. Uh-oh.
Uh-oh, we're in the infinite regress world.
I was the wrong thing to click on.
This has happened to me.
I don't know how to exit it. Okay,
Oh,
cool. We're back in normal mode. Okay.
okay, someone has joined us. Do you want to introduce yourself?
Sure, I'm Nancy. This is
Lisa, you want to say hi? Okay, we're just getting started. They're talking about their copycat drawing robot, and we just saw a little bit of the Arduino code that they use.
right.
Feel free to ask questions in the text chat if you'd like.
So we can also like quickly show like our ultimate goal with the robot arm. So okay. So this is ultimately what we were able to accomplish. And so if you think about it, it's actually a little bit tricky to, if it loads, because your arm fundamentally is working in theta coordinates. You give the servo, there's two servos, and you give one a theta command, and then you give the other a theta command. But generally, when you're drawing or doing anything, you don't think in terms of theta commands, you think in terms of XY commands. So this is it drawing a narwhal, but the way you can think of it is like, stop this. The way you can think of it is like you have your arm or whatever, and so you don't exactly think in terms of like, oh, and I want to like turn my arm 90 degrees and then turn my wrist like 10 degrees and then, oh, I've reached this position. You think of it, that is forward kinematics. You give it two thetas and you're like, oh, I'm at this position. But actually what we think of in terms of is like, oh, I want to like grab this tangerine. And so I reach for this tangerine, which is my desired like coordinate, XY coordinate, and then I sort of, my brain sort of automatically calculates the thetas that I need in order to reach that position. So basically, a little bit of trigonometry is needed to get from the thetas to the XY coordinates that you want. Yeah. So, oh, the link. So that's the code link, and then this is the YouTube of it doing like inverse kinematics successfully. I guess we can talk about it like how ideally it works, and then we can go into the issues to be encountered in terms of practically implementing it, and then trying to apply it to a way that's consistently mass manufacturable, which is also an issue. Yeah, okay, so, right, so we have this, like, concept, which is, like, you can have this very simple robot arm that can draw things. So it's this, like, planar, it just involves 2 degrees of freedom, and we're saying that it's enough to be able to draw whatever you want. So now the question is, how do you go about like, learning inverse kinematics? So it turns out in the 2 degree of freedom case, it's pretty straightforward. I guess I guess we write it up.
I think you just use
Oh right, okay. We use this PDF we've done that some professor wrote somewhere randomly, and then I stared at it for like a few days trying to understand it. But it's actually pretty straightforward once you understand what all the variables are standing for. But I don't know, the basic idea is pretty straightforward. So if you just have 1 degree of freedom, it's pretty straightforward. You have a triangle, right? You're like, okay, this is the XY coordinate I want. And then I can derive the angle I want pretty straightforwardly based on, the X and the Y coordinate. You just like take the arc sine or the arc cosine, and then you can figure out the theta you want. But it becomes a little bit more complicated when you have 2 degrees freedom, because if you maybe this is a better angle. So if you have 2 degrees of freedom, because you can hit this point here in 2 ways. You can hit it in this like sort of elbow down case, but also if I can demonstrate, you can also hit it in this elbow up case. And so yeah, you basically just need to, oh, you sent me the PDF thing. You basically just need to decide and pick one. And so this is the PDF, and it has this image in particular. Is it on there? Twitter? No, probably not. Okay. Go to PDF. So yeah. So you just need to like pick one of the 2 cases, and then basically just you work out the math, and then you just code it, and then it's done, and it works. So let's see.
You make it sound a little easier than it actually is.
Maybe. It took us a lot of trial and error to figure out what was going on. So this is, if I can screen share for a second, this is the elbow up and the elbow down diagram. So you can see for the same xy coordinate, there are 2 possible, and also given, a set length of integers, there are 2 possibilities for reaching that position. So you sort of just have to account for that. Also, we had a lot of worries, I guess, in terms of practical implementation, because all the implementations we saw online were using like continuous rotation motors, like not hobby servos that are limited to 180 degrees. So that constrains basically like the area we can draw in, and we are worried that would sort of interfere with algorithms, but it doesn't really. So there's like a little bit of math here, but basically the solution is given to you, and then you can just put it up, which I think I have. If I'm still screen sharing, I can show you guys this. Copy that. I don't Okay, so we have a lot of code files here, and we haven't worked on the code itself in a while, so we've sort of forgotten. So you can sort of see on the screen basically what's going on. So it's the same as the code we showed earlier, and this code will be put up on GitHub just soon. Hopefully we'll get around to it very soon, after we clean up the code a bit. But basically the idea is that you have this get angles function, and you give it an xy coordinate, and then it just does the math to figure out the theta you want. So once you've coded these 4 lines of code, you're done. That's basically all you need. Because you can see here, yeah, so this is just the sort of the square root arctangent function that was in the PDF I showed you earlier. And then all that happens is if you, for instance, want to draw a line, you just give it this sort of, you just give it this like series of xy coordinates that is the line you want, and then it draws it, and that's great. So yeah.
I'm sorry. Can you show the code again that shows how the trigonometry translates into Arduino code?
Sure. So I don't know if it's visible here, but this is the code right here, which I'm highlighting from line 30 to 37.
We're not seeing it. I think you have to stop screen sharing and then start it again and select the page that has the code.
Sorry, you guys have been staring at the same thing this whole time.
Okay, there it is. There it is. Oops, hello. Okay. Here we are. Infinite percent. I saw the code for a second there.
So I think I'll share my desktop, and then that should be the correct thing. So from lines 30 to 37, if you see it now, that is the code. That's all you need in order to get it drawing what you want. So.
The same as if you look at the PDF that we sent in the 5.1.1 Ultimate Solution section. It's like the
Well, this is quite beyond me, but I'm sure that people who are a little further along in robotics will be interested in how that translates. Thanks.
Sounds good. Okay, so you have these sort of data, and so there's just some shorthand in the documentation to get used to, but it just says cosine theta is equal to this and sine theta is equal to this. But so then when you turn it into code, you can see here we say cosine theta is equal to this and sine theta is equal to this, and blah blah blah. You take the arctangent of the sine and cosine and get the theta. So okay, so after you figure this out, it's not all bunnies and rainbows, sadly. So yeah, I guess at this point, I don't know, do people have any questions, or do we just continue talking about the horrors of trying to get this working with low cost like servo motors?
Lisa, did you have any questions? You can ask directly if you want by unmuting your microphone. There's a little gear. There you go.
Oh, wow. It was just so I saw that same paper and I tried to implement it, but I found because there's only 220 degrees of freedom, you can only have like one of the solutions. You can't do both arm up and arm down, right?
Yeah.
Okay. So.
For since the servos are like slots, it actually makes it easier because then you don't have to like make sure you're looking for the correct solution. Because like it could be solving one way and then based on the next step it can switch, and so then instead of making a nice smooth arc, it like switch into elbow up.
Like this drawing, and then it's like went up.
Yeah.
But yeah, we just fixed it as up or down in our solutions always, based on which like one thing would give us more area. Yeah, you can actually see it in our code. I can screen share again in a sec. Button, screen share, open it. Okay, so.
I think tonight.
How do we get rid of it? Well, at some point in time, we had this constant, which was just like always solve up or always solve down. And I think ultimately we probably resolve it in the end without.
Or it's just like hardware thing. And so, look,
yeah. So, yeah. I guess we should also mention that there's a helpful instructables, but they use 360-degree motors. So yes. So this one, you can see in her code basically she has like an up or a down somewhere. Okay. Let me just oh oops. I forgot to fix it. Cool. Yeah, right, precisely. Because the servo you are just limited to one solution, and it's actually to your benefit since you don't have the edge case where you can only either like or you don't have this case where you may potentially have two solutions, and if you don't have like a smart way of picking between the two solutions, then you can end up like, oh, I'm here and drawing a line, and then like your servo's whack up and be sad. Yeah, are there any other questions?
No, I'm good for now.
Okay, cool. Yeah, so I guess we can talk about our practical, like when we try to implement it, all the issues that we
So one thing that was very helpful was I used Octave. You can also use Python to plot where your servos are actually capable of going. Because if you just kind of send x, y coordinates to the servos, at times you'll be confused why they're not behaving like you want them to, and it'll be because you're sending coordinates that they can't. So plotting out, like measuring where the servos, like the full range of the servos, measuring out like where exactly the point of the servos go, and then plotting everywhere it can go is very helpful because then you know exactly what the
Yeah, I think we have a picture. Perhaps? Yeah. Where else would we find a picture? Is there a picture in the PDF? Okay. I think there's just a picture somewhere on my blog. Ooh, we can show pictures of what it looks like at the beginning. Okay, so there are also these sort of issues that you encounter because you're not working with ideal motors. You're working with these really crappy, like $5 hobby servos. And so these sort of issues, if you look at this picture, what you can see is a lot of jitter. Oh, here we go. Okay. So you can see there's a lot of jitter. This is like us trying to draw a circle and trying to draw a straight line. And you can see that there's a lot of jitter. And additionally, at that point in time, it was drawing a straight line instead of at a diagonal, which took a little bit of like figuring out. So what you'll be able to see from the screenshot here is us trying to resolve those issues. So what you can actually see is a bit of Python code run in IronPython in order to help determine, you can see in the lower right corner, the sort of yin-yang shape is actually representing like the full, like all the possible positions that the robot arm can reach to. So, yeah. I guess I could, yeah. I'll link to this blog post for now, but it's kind of long, so for like future reference or something like that.
So you said that you've taught in-person classes to people to build this. How long does it take? How many classes? How many hours?
Okay, so what we taught this class a few times. We taught it to some high schoolers over the summer as part of this MIT Slack or Short program or something. And so that was 6 sessions at an hour each. And so basically you pick up one session and you just build the thing with the like kind of mock robot arms, which shows you the basic idea of where you can like, you know, control a robot arm using these rotation sensors without all of the trigonometry and image kinematics. And then we tried to cram like the inverse kinematics into the next few hours, and that was not great. I mean, like the high schoolers chose to be in our class, but it was still summer, and I think they were just like kind of like, I don't know, zoned out a little bit. They weren't like, oh, it's like only half a page of math. They were like, oh, this involves trigonometry. And they kind of like tuned out. So I guess our next attempt was where else did we get?
We taught it
Oh, to the New Jersey. Okay, we taught it to some homeschoolers in New Jersey, so we skipped the inverse kinematics portion because that was a wide age. So that had people like in middle school. And then our latest attempt is to teach it online. But again, we decided to, yeah.
Still getting it up there. It's even more difficult to explain when you're not in person. So you just try and be very careful and explain it very detailed.
Yeah, so it's showing up in our online course, which is currently closed, but the way we structured our, I guess, just everything is all of our hardware and software will be in the public domain. So the hardware is released in a timely fashion, but the software, it takes us a little longer because we have to comment it. And then the class is released publicly for free a year after it becomes available to people who ordered us on YouTube or whatever. So that class will be available for free sometime in the near future, next February. And hopefully it'll be like more invited by people. So yeah, that's our plan.
What else do you plan to do? Do you have other robotics projects that you plan to teach people?
Yeah. This is one we're working on for MIT class.
The little robot vehicle?
Yeah. He's got some IR sensors and some cute photodiodes on the top.
So does it avoid objects? What does it do?
Yeah, it can. It drives around, like it'll be able to wall follow and it can detect other objects. Also, so these photodiodes, you can shine a light source and it'll follow the light source, like kind of like a little pet robot. This is one we're working on for an MIT class. So probably won't have a course up for a while.
I think like they're going to use these robots in the classroom this fall, and then the hope is the online class will follow the term after that next spring.
Right now, we're working on Stormbot, but we've just barely started. This is our Stormbot right now. Just one motor.
It's an adorable tiny motor. It's sort of amazing what you can find online. This little stepper.
These are apparently stepper motors used in cameras.
For like zoom, in fact.
Shutter zoom. And we're going to try and use them as wheels for tiny robots.
Yeah. So, I guess, yeah, that will be our next class. Will be multi-robot formations. So, robots making figure 8 or doing other 3D things.
Well, feel free to use this platform. Just if you log into Hamago, you'll see that there's a Create a Geek Out link, and take it away. It's pretty easy to do. You know, the only limitation is that it's up to 10 people at a time. So if that's not a problem, then it's got a lot going for it. You can use the whiteboard to show diagrams, and you can see the screen sharing sometimes has a couple of glitches, but you can use that to show code as well.
Yeah.
I actually recommend putting stuff in the chat bar for links and videos and whatnot, so people can use it in their own full screen. Although I'm happy to announce that we do have a Chromebox now. Although we're still getting it set up.
Are the links archived? Is the chat archived?
Chats are not archived, but we can take notes, I believe.
So, could you post the actual code for the equations that you used?
It is. Oh, the kinematics isn't up yet. Yes. by this Friday, we will be able to accomplish this.
Yeah, it'll be on the. It'll be at the GitHub link.
It will be at the GitHub link, so if you just check that before this Friday. If people are interested in it, we can definitely get it up sooner.
You just want the function, or
Yeah, so I tried writing it, and I guess I got the equations slightly wrong. So here's my thing. And then, like, these are kind of two equations I got, which I guess I used the same paper that you guys did, and I'm not sure why. I don't know.
Modules.
At least I think I used the same paper.
Which file inside this repository?
I'm sorry, right? The V1 RoboArm V1.py.
Okay, RoboArm V1.
All right, I just checked it into different modules. So if you actually go into the modules directory, and under arm manipulation, line 46 and 47. But I mean, if you post the stuff on Friday, I can just look at it there and figure it out.
I also just posted the function in the chat bar.
Yeah, if you copy and paste it, it'll be formatted better.
Cool. Thanks.
Yeah, no problem. Okay. Yeah, that's all we're using. That's all that is there. Oh, right. In terms of like practical issues implementing environments, I'm sure you've run into them already. We had a lot of issues that were never completely resolved. We also wanted to keep our design very, very basic. Like it's like something you can look at and you can immediately say, "Oh, I could totally build this," because we wanted people to be confident about building robots and about how easy it can be. And so we restricted ourselves to entirely laser-cut 2D sort of things. And so this resulted in a lot of issues for us. So I guess the technical term for the way we implemented it is these things are cantilevers. And so you can see that there's like a lot of up and down wobble. And additionally, the servos themselves have a lot of gear turn wobble. So you can see this because without like turning it, you can see that there's a lot of wobble sites as well. So this creates issues when you're doing the drawing because whenever you change positions, like if you change from rotating counterclockwise to rotating clockwise, then you get that extra slop in there. And so you can see even with the narwhal drawing, there's like a lot of slop in it that you really can't resolve. Another
things that helped the data though was we made the arms, we kind of restricted them to be pretty short. And we also, at first we weren't using the servo horns. We were like laser cutting our own shapes, but the servo horns produced jitter this way a lot. And another thing that helped us, we switched to these are digital servos. They were just like way higher torque than the analog models we're using, and they also helped reduce jitter, but they're still pretty jittery.
So yeah, it's not an ideal solution. Another really helpful resource is Theramino. The Theramino papers. So there are these Theramino papers, and they actually talk about the actuators they use, and they specifically mention trying several different motors. And then, because the thing about hobby servos is there are no data sheets for them anywhere. Like, if you ask the manufacturer for a data sheet, they'll just see, like, they'll just look at you kind of strangely. In a broken English kind of way. And so, it really just comes down to trial and error to try to find like a servo that is even like semi-okay for your usages. So the Theramino is able to get way more accurate and less dirty pictures than we were. And even with a similar style design, you can see they used a sort of vertical design. So they had the vertical design arm, and then they had a rotational degree of freedom. And so they just trial and errored and found this like servo, and we wanted to buy this servo as well, but it was out of stock. So we just ended up picking this ESO8E servo because it seemed sufficient and it was time to launch.
Yeah. The Theramino people are also really nice. If you email them and ask them questions.
They will totally answer all your questions. I don't know where they find the time to do so. They're like super helpful and friendly. And they have a few papers on there about their setup, which we found pretty useful. Yeah. So they answered a lot of our questions. And I actually send the link to the correct one. Did I include? I don't know. Oh, the paths. Okay, yeah, I did include the motors helping. So you can see down there, they had the MG958 that they thought was the greatest thing ever. Wait, was that the one? No. Okay, the TGY930 is the one they found. Anyway, so yeah, they built this awesome robot arm. I don't know. Yeah. Other issues. There are software issues as well in terms of like how you translate from an image. So if you want to do something such as you draw a picture that you have on the screen, and you don't just do it live, like it's not like you're tracing this drawing and then the robot arm is tracing it, but rather you have a picture like a selfie or something. How do you draw that picture? How do you translate it from a full RGB color image to a XY image? Like I don't even know how to describe it. Black and white image. Right. So basically, what happens in the end is you have to do edge detection on the image to find the edges you want, and then you can measure. Yeah. Oh, we just sent change the coordinates. Okay. So the thing you might do is like turn those into vectors. So instead we just sort of sent, XY coordinates because they were on the line.
We never got full color images working that well because if you just want to send the string of coordinates to the robot arm, you have to make the line 1 pixel wide. And this is like rather difficult because sometimes the edge detection would look very much like it's on the edge, but there'd be two lines separated by a pixel or something. So you get a lot of coordinates or trajectories that were just small dots or small lines, and instead of just nice curves.
I guess like a good example of us trying to do it is we can hopefully this, okay, here we go. So here's a kind of terrible picture. So this is right before we were going out to visit Lady Ada. She runs Ada Fruit, and so I was like, whoa, we should totally get a robot arm to draw her face. But it sort of failed, which you will see if you watch the video. I mean, it did fail. It didn't sort of fail. But if you skip ahead, you can sort of see. Basically, we took the wired picture that you can find on Google Images, and then we did edge detection on it and asked our robot arm to draw it. But it's like very, I don't know, it's just very hard. we never really fully solved it. And then it turned out that people were pretty excited by it. So that's where like running the class in person before putting it online helped. Is we found out that people, at least high schoolers, were pretty excited just by the sort of like robot arm that like, like copies whatever the other arm is doing. They're pretty excited by that, and yeah, we went for the excitement over sort of the gory technical details of how you do inverse kinematics and like edge detection, canny edge detection and things. I don't know. We would have been happy to run the course on that if there wasn't as much. But we're happy to talk about it all day long.
Issa, did you have any more questions for them?
No, I'm good.
Great. We have some other robotics geek outs coming up. If you look at Arduino, nothing as advanced as what you're doing. Mostly on the order of getting started with simple robotics kits.
Cool.
So maybe when you've got another project, you'd like to come and do another geek out. Be happy to do that with you. And as I said, feel free to create your own for your own classes.
Yeah, you could do it in about stepping. That's early.
We're learning all about steppers and Bluetooth right now.
Yeah.
Maybe in the near future there will be a geek out about the pains of working with Bluetooth.
Well, I like that you're having so much fun with it. Thanks a lot for taking the time to show us.
Thank you very much, Anna.
Thank you.
Good luck with your robot arm project. Make sure to tell us about it.